All right, my AB children, here comes section 6.3 on summation notation. Kind of sounds like a rhyme there a bit. I can tell you that this is a bit of a goofy section. It's all, again, about notation. If you catch it, cool. If you don't catch it, don't stress. This is usually like a one-question, multiple-choice type thing on the AP exam, so it's not a hot topic. The Riemann sums that we did in the last section, they're a hot topic. They come up quite a bit. This particular section, not so much. So if it's good for you to see, and the concept behind it is important as we get into studying integrals. But the nitty-gritty of it is not overly significant in the scheme of AP Calc. But here's the story. The graph of the function f of x is shown below. How can we approximate the area under the curve in the interval from -1 to 6? Create a Riemann sum with n sub-intervals and have n go to infinity. What the heck are they talking about there? Well, let's break up our graph going from -1 to 6, right? And the area we're talking about is all of this. And then we come under the curve over here. Remember, that gets subtracted. That's a subtracted value. And then we get above the axis over here again. Okay. This is the area that we have. Now, how many rectangles can I put inside of here? Well, if I'm going from -1 to 6, let me just say I'm going to make each one worth a width of 1, right? So I'd have 1, 2, 3. This one actually goes above and below. And then I've got this guy here, right? So if this were then how I subdivide it with, what did I make? 6, 7 intervals, right? 1, 2, 3, 4, 5, 6, 7. 7 intervals. I could calculate out, and I would make my Riemann sums. It didn't say left or right. It just said divide it up into the rectangle. So I could make my left Riemann sums. I could make my right Riemann sums and divide it up. But what if I were to put, instead of 7 intervals, what if I had 14 intervals? Then each of these gets split in half, right? Half, 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 and I'm picking nice values here. So that's what it would look like. Now, is that going to be a better estimate of the area under the curve when I put those together, or is that going to be worse than when I had 7? And the answer is it's going to be way more accurate with more rectangles. So if I have an infinite number of rectangles, that's what this is talking about, an infinite number of rectangles, then how accurate is my answer for the area under the curve? And the answer to that is that it's extremely accurate. Infinite number of rectangles gives me an extremely accurate value for the area. And that's the big concept that they want you to get out of this, that the more rectangles you use, the more accurate your answer is. All right, so that's what this section, the overall big takeaway should be. And it kind of makes sense. If you divide it, keep dividing it. And I think actually on the video from the curriculum people, he actually did that and showed you on a picture what it would look like when you've got more and more and more rectangles involved with it. But I think you got the idea. If n is the number of subintervals or rectangles on the interval from A to B, what's the width of each subinterval? Well, we talked about this before, right? The width of each subinterval is that formula that we used, b minus a over n. That didn't change. And what this actually represents is the change in x, how x is changing, how wide, how that subdivision is. And notice that it's talking about it all along the x-axis, the change in x, the width of your rectangle. We're going to see that noted in the notation as delta x. That means the same thing. It's the change in x. And then if n approaches infinity, if the number of rectangles approaches infinity on the interval, what does the width of each interval look like? What does it approach? Well, how wide are you getting? What's your change? The more, when I had just a single unit here, it was wider than this half. If I were to divide it again, it'd be a quarter or something like that. So the width of my rectangle, my delta x with more rectangles, actually the width gets closer to 0. Does that make sense? My width was 1, and then I added another rectangle, now it's a half. And I added another rectangle, and now it's a quarter. And I add another rectangle, and now, do you see where it's going? It's getting smaller and smaller and smaller. The width of my rectangle is going towards 0. And so that's going to be part of our notation. So the sum of the area of all the rectangles gives you the area under the curve. We know that. So it's going to be this. For rectangle 1, it's going to be delta x sub 1 times, remember it's length times width, so it's going to be how wide it is times the length of it. And the length of it you find by figuring out the y value, right? So this is a way to represent rectangle 1. So the change in delta x1 times the y value for x1. Well, what would it look for the next rectangle? That would be a delta x sub 2 times f of x sub 2. Right? This would be now rectangle number 2. And you can keep going, right? Rectangle number 3, delta x sub 3, f of x sub 3, and so on and so on and so on, until you get to the last guy. And the last guy is going to be delta x sub n, 100, 1,000, 10,000. You could have how many rectangles, right? We said an infinite number, times f of x sub n. And we can represent this area by combining limits with summation notation. And what they're talking about here, you probably haven't seen this symbol before. I don't think you have. This is a summation symbol. This crazy looking, maybe looks a little like an E. And what it means is you take and you keep adding each term after it. Like we did here, you take the first guy, what it is for the first one, and you add it with what it is for the second rectangle, and you add it with what it is for the third, the fourth, the fifth. However many rectangles you have, you're just adding them up. So this is a summation, notation. The area under the curve of f of x on the interval a to b is represented by limits. We're not done with limits yet. Because how many rectangles could you have? An infinite number of rectangles. So my limit as the number of rectangles gets closer to infinity equals this. b minus a over n. Isn't that the width of my rectangle? My delta x times f of a minus b minus a over n times k. And you're like, what the heck is that? And I will show you. Where n represents the number of rectangles, subintervals, and there's an interval from a to b, and k represents the kf subinterval, whichever subinterval you're in. So subinterval 1, subinterval 2, subinterval 3, whatever that might be. So another way of writing this summation notation is this way. The limit as delta x approaches 0, the width of the rectangles gets smaller. The sum going from k, sorry, not n, k equals 1 to n is the top number, of delta x, the change in x, your width, times f of x sub k, whatever rectangle you're with. So the sum of the length times the width. So first rectangle is a 1, second rectangle it's a 2, third rectangle, however many rectangles you can make. And again, this is a notation thing, so if it's messing you up, just take a deep breath, it'll be all right. All right, next page. They give you the definite the definite integral notation. And so there's a way of going from, and this is what we're looking at today, summation notation, going back and forth between that. How's it written then in integral notation? Remember there was like a conversion. It reminds me a little bit of like when there was a conversion between logarithms and exponents, how you had that certain way of going from a logarithm to an exponent, or an exponent to a logarithm, how we did those loops and such to be able to write them from one to the other. This kind of reminds me a little bit of that. But when I put it into this limit formula that we just talked about, when I put it together in this form, it's actually written as an integral. Here's what an integral looks like. It's that fancy pants S kind of thing. You see them painted on my wall in my classroom. The lower limit is A, the higher part is B. Now A and B come from your interval, so that's no big deal to you. It's just where you're putting them, the location of those things. And that is then the integral of your function. The dx means with respect to x. And guess what this actually is? The area under the curve. The area under the curve on the interval from A to B is represented by that exact same thing. That's what integrals are, the area under the curve. All right, here's where it gets a little odd in the midst. But we want to rewrite this definite integral using summation notation. Well, the summation notation is this way. This is integral notation. So you see, this is my summation notation. Maybe I should put arrows. This is my integral notation. I want to take it from integral notation and write it as a summation notation. So I need, some of these are standard all the time. Beginning is the limit as n approaches infinity. And then I make the summation sign with a k equals 1 on the bottom and an n on the top. That's going to be standard for all of these as you're putting the notation together. Well, b minus a over n means that I have, here's my a's and b's. B equals 6, a equals 2. So if I take my b minus a over n, for this guy, it's going to be 6 minus 2 over n, which is a 4 over n. That's what comes next, 4 over n. And then it is f of, so I'm going to put, I don't need the f in there. It's going to be, because I'll show you why in a second, my a is 2 plus my b minus a over n is 4 over n. That's times k. Oops, yeah, that's good. This whole thing right here is what I'm going to be doing with this. So that I'm taking this is like my x. So this is like my x squared. I probably should put another set of brackets in. This is like my x squared piece, this piece right here, which means I then need to square that quantity. And then I also have a minus 3. So let me finish this out and then I'll see if I can explain it a little bit more. That's my x squared, and then I still need my minus 3 there. All right, so the b minus a over n part is really not a big deal. That should not be too much pain to you, but this is kind of goofy. This part in here is goofy. So you're taking 2, my a value, plus your b minus a over n times k, but you need to do to it whatever the x is being done to. If you know what I mean. This x is being squared, so this has to be squared. And then you have a minus 3 at the end. So this is equivalent to x squared minus 3. All right, let's see if we can try it going the other way. Now they give me the summation notation, and they want to know what's the integral look like. So if I'm looking at this, I know that my b minus a has to equal 6. Do you know what A is? And I do if I look over here, right? A is 4. If A is 4, sorry, I should have put the 4 in. Then B equals 10. So one way to write this, if A is 4, here's my integral notation, A is 4, B is 10. This is my B minus A over N. This represents my X piece, right? 4 plus B minus A over N times K. And what are you doing with that piece? You're squaring it. So this would be X squared, and then you need to have that with respect to X at the end. By the way, Mr. AP takes points off if you don't put the dx at the end. So one way to write this would be in this format. Second way, now these are all equivalent forms. These are all equivalent forms. Another way you could write this is 0 to 6, because remember you have to have a width of 6 for this. And this would be 4 plus x quantity squared. This piece would be your x piece with respect to x. And I'm only showing you this, I'll tell you why in a second, because there's one more. Another way you could write this, oh, this is a plus, right? Plus, yeah. Another way you could write this is 0 to 1 with a 6 factored out of 4 plus 6x quantity squared with respect to x. These are all, and I'm going to put it up here, equivalent forms. And you know how that comes up in multiple choice questions and such, where they might give you one format versus another format. This is just with the 6 factored out. If I take and factor a 6 out of that whole thing, that's what it would look like. So they're all equivalent forms. Any one of them works pretty much the same. So different ways to write the same exact stuff. Whichever one makes the most sense to you, go with it. Okay. Number 3. This one is goofy too. I've got the limit as 2 over, as n goes to infinity of 2 over n. And then it gives me this whole craziness here, right? And it says, assuming that the lower limit a is 0, write an integral that represents the above expression. All right, so now again, I'm going from this crazy limit form to an integral form. So I want to write the integral form. Here's my integral form. They tell me the lower limit is 0. I know that this, too, represents b minus a. Oh, equals 2. And I know that a is 0. So that means that b has to be 2. There you go. There's your upper limit. And here's where you have to take like a, you kind of have to narrow your eyes in to see what the function is. And so I see everybody's got a 1 and it's a fraction. Okay, got a 1, got a fraction. But see the value that's changing each time? That really represents your x. So really this is like an x, and then all of them have plus 3's. That's your function. That's your answer for this guy. That's your integral notation. You're taking an x value that's changing and you're adding 3 to them. So here's another one, number 4. The expression 1 over 10 cosine of 1 over 10 cosine of 2 over 10, and you're adding them all up, is a Riemann sum approximation for what definite integral? And so I'm looking at this. I want to set it up as an integral. This one goes, if I think of the expression 1 over 10, the bounds for this one go, because these are positives, it goes from 0 to 1. Remember how the cosine function goes? Cosine only bobs and weaves between -1 and 1. And the reasoning, because if this is 1, and you've got a b minus a that has to equal 1, then you've got values of 0 and 1 as your a's and b's for this guy. What function do we have? We have the cosine function. What's the changing part? Changing part is x. But you can put that in parentheses, you don't have to, with respect to x. You're not doing anything else with it, so it's just an x. So there's your integral for that guy. Where is the 10, and why isn't it in the integral? The 10 is down here, right? It's in your denominator. And 1 over 10 represents b minus a over n. So what does the 10 represent? 10 is represents the intervals, how many subintervals you have. So 10, how many rectangles you've got, represents the number of subintervals. It has nothing to do with the function. It just is telling you how many times you're going to divide it up. You've got 10 rectangles in that one. All right, that is, my friends, summation notation versus integral notation. And we're going to look at a couple problems and then call it a day for this one. Number 2 is the first one. Okay, so we're going from the summation notation, and they want us to write it as an integral. So my answer is going to be an integral. They tell me the lower limit is a -3. That's my a value. The 5, they don't give you a lot of space. I'm going to go up here. The 5 represents my b minus a. But you know that a is a -3. So b minus a -3 equals 5. b plus 3 equals 5. When I take that and move it to the other side, I get a 2, right? b is 2. 5 minus 3. All right, there's the beginning of my integral. This whole thing in parentheses represents your x. So this whole thing is your x. What are you doing to your x? You're taking the cube root of it. So this one is just the cube root of x with respect to x, and you're done. All right, now they want you to go the other way, and they want you to write it as a summation notation. My next one I want to look at is number 5. I know from my bounds, this 5 is b, a is 2, b minus a is going to equal 5 minus 2, which is 3. Yeah. I'm looking at my other answer key, and I have it as a 2. It's really a 3. Okay, so this has to have the limit as n approaches infinity. It has to have the summation symbol going k equals 1 to n. And then it's going to have my b minus a, which we said is 3, over n. I don't know how many subintervals there are. And then it has to be multiplied by, here's where it gets a little dicey. The 1 is my numerator. See how it's 1 over x? So I'm going to have 1 over, and my x is a, -3. No, I'm sorry, my a is 2. My bad. My a is 2, this bottom lower limit, 2, right? And then what's happening with this thing? Then I have a plus, right? Then it's the b minus a over n. Well, that's 3 over n times k. And that's it. I'm not squaring my x, it's just the x's in the denominator. And so that's my summation notation. All right, last one is number 8 that I want to look at. Number 8. The expression yada yada is a Riemann sum approximation of which of the following integrals? So they want you to figure out which integral this fits. And so I'm looking at the numerator here. I know that my b minus a has to be 3. Well, that immediately knocks out c, right? I don't have c. This one's going 0 to 21. This one's 0 to 3. This one's 0 to 3. This one's 0 to 3. So I know that I have to have that any of the rest of those, A, B, or D, are going to work for this guy. Let's figure out the next thing. I've got my changing values are this one in front. And remember this 7 over here, this 7 in the beginning is just telling you how many subintervals you have, so you can ignore that in the midst. But this one is 3/7 and this is 3/7. Then it changes 6/7 and 6/7, 9/7, 9/7 down the line. And so the changing piece, remember we saw in the other problems, the changing piece is called your x. So the 3/7 is x, and then you have times a sine of that same value. You've got the same number in front as what you have that you're taking the sine of. So which one of these fits? The only one that does that is A, and that's your answer. It's not this one with the 1/7 because the 7 is part of your x value that's changing each time. 3/7, then it's 6/7, then it's 9/7. So that's a changing value. So you're not multiplying by a 1/7 and then the whole thing. I think B would be the other thought you could have for it. But like I said, the x is part of that changing piece. So that's it. X times the sine of x, going from 0 to 3. And there you go, section 6.3, summation notation. Shoot me an email if you got questions. I'll see you in class.